this stuff out of the way. Good afternoon, lads and ladies. Welcome back to MAC1140. That's pre-calculus algebra. Today we're going to finish our discussion on polynomials. We do still have what looks like a meaningful amount of material to go through in the textbook. We're just looking at section numbers, but believe it or not, this is going to go real quick. So today is lecture-wise not super intense, but the associated homework will take a meaningful amount of time. I did put together your new homework. I haven't released it yet because I'm looking to see if I can get in there and trim it down a little bit. Because it is going to be due on Wednesday. So let me come over here. Get this out of the way. I also did finish grading your tests. The last few I just finished grading like 30 minutes ago. So if you haven't checked today, you may want to check. There were a lot that I didn't have done last night, but I do have done now. All right, there we go. And the good black pen is maybe this one. All right. So let's go ahead and turn on the screen share. I'll bring you guys over here. This is, of course, MAC1140. Just pre-calc. This is a lecture, and today is the 19th of July. I noticed that the announcement in Canvas from last Friday had the wrong date. It said the 14th. Of course, that isn't correct. So I've gone ahead and fixed that and uploaded the video from that day. So you'll see in here. This one previously said it was the 14th. Of course, that's not true. It was the 15th. And I did go ahead and upload that lecture. It might still be processing. Yeah, it looks like it's still working. But it'll be up there for you soon if you missed that or if you just want to review that. Let's come back over here. So today, we're going to do a few things. We're going to talk about exam 1 stats. The test went fairly well. Then we are going to cover section 3.4, which is on the real zeros of polynomials, real roots, zeros, whichever you choose to call them, polynomials. And we're going to talk about section 3.5, which is complex roots and the fundamental theorem of algebra. So you know the word theorem is always a big deal. When you see the word theorem in mathematics, that means it's a true statement that's important. The fundamental theorem, now that must mean something very serious, and indeed it does. But we'll work our way into it. Don't panic about this thing. It sounds, for your purposes, it's important, sure. But the real reason it has this special name in front of it is because its proof is quite hard. It's one of those things that does underlie everything we do. But sort of one of the things that elevates it to its very special status is that it's quite hard to prove. So we won't be proving it, unfortunately. That is well beyond the scope of this class. But we'll be discussing it and its consequences. First, though, exam 1 statistics. In case anybody missed it, right? Of course, exam 1 was last week.
You're muted, sir.
All right, sorry about that, guys. I got a thunderstorm rolling through here. I think it knocked out my internet access for just a second, but it looks like we got pretty much everybody back. We were going to do this. So these are the things we're doing today. We're going to begin by talking about the statistics for exam 1. And I was loading those just as
You're
my
still lagging. We can't really hear you still.
What I was saying is that if you missed exam 1 last Monday, today is your last chance to make it up. Right? As we talked about in the syllabus, If you miss a test, you just need to reach out to me, and as long as everything is reasonable, I will schedule a makeup exam for you. Still lagging. That's not good. All right. I will try to speak slowly and clearly. If there's anything that you miss coming from me, you're unable to hear, let me know in the chat.
Yeah. We can't hear you. Your internet connection is still bad.
You're muted, Professor.
God damn it. Okay, now we're back. We're on my phone's hotspot this time. So everybody hear me okay?
Yeah, now it's working.
Okay, good.
Yeah.
All right, sorry about that. Remember to tell Cox Cable how bad they suck. So we want to talk through the statistics on exam 1. What I was saying before I was so rudely interrupted by the shittiness of this internet connection is that if you missed exam 1 for whatever reason, today's the last day to make it up. Like the syllabus says, if you miss a test, just reach out to me. Tell me what happened, and 9 times out of 10, I'll schedule you for a makeup, but we got to do the makeup within a week of the original test. So if you missed the test, today is the last day to make it up. Come to office hours. Okay. I'm going to look at the stats for the test. I haven't looked at these myself yet because I just finished grading it a few moments ago. But I always like to share this stuff with you guys. And this looks good. This actually looks really good. The average of 70 is higher than normal. We've got a pretty standard distribution here. This is about what we want to see. And most folks did pretty well. This one caught a large number of people out. This is a tricky question, but we did address this in class. Transformations all went really well. Shifting affecting the range went well. Relationship between points on the graph and the inverse. Inequalities went well. Oh, I'm very proud of you guys. So overall, grading it, it felt good to me. And looking at these statistics, continues to feel good. This one caught some folks out, and most of the trickiness, I think, is in the function notation, sure, like making sure you get this right, but also in simplifying, doing the algebra work to simplify this. Now, we have done a bunch of these in class, and I don't want to burn more class time on them. But if you are having trouble with this, look at my feedback. If you got like less than, say, 7.5 out of 10 on this one, come by office hours and talk through a few of these with me, work on a few of them with me. This one was a little bit tricky too. There were a total of 4 minima, 1, 2, 3, and 4. We went through this one in class last time. I think maybe last Tuesday. This one, most folks did pretty good, just more transformation stuff, more function notation. I think everything else went fairly well. This was the other one that seemed to catch a number of folks out. And I just want to remind you that the way you show a function is even or odd is to look at f of negative x. So I've made a lot of comments on your work. If you go look at your written work, everything is annotated with lots of little things written in. If you made a mistake, I've got corrections there for you. So we don't need to burn more time in class going over the problems themselves. But I'll remind you to please look at the comments on the written work. So exam 1 is graded. Look at the comments on the written work. There's one other thing I want to say here, and I had a handful of folks submitting very little written work, and I want to remind you that the free response problems, almost all of the credit comes from the written work. We did talk about this in class. 8 out of 10 points on each of those free response problems comes from your work. So if you don't write any work, there are a few exceptions here where I said, just type this or whatever. If you don't give me any written work, I can't give you credit. For example, on that last problem, if you say the function is odd without any work backing it up, that's only worth 2 out of 10 points. So you need to show me your written work. It's absolutely critical. All right, that's enough about the test. If you want to talk more about the test, come by office hours, send me an email or Canvas message. I'll be happy to do that. the place we're going next is to section 3.4, which is on the real zeros, the real roots of polynomials. We've shown, or we've discussed the relationship between roots and factors, right? We know what that is. I'll say recall. TFAE, the following are equivalent for a polynomial P of X, 1. X equals C is a root of P. 2. P of C equals 0, i.e. X equals C solves P of X equals 0. This is why some people call roots solutions. 3. X minus C is a factor of P of X. And then the last one was the remainder when we divide P of X by X minus C is 0. And that last one connected to something called the remainder theorem. We saw that last time, that said the remainder when you divide P of X by X minus C is always equal to P of C. So if C is a root, then that means P of C is 0, so that remainder would be 0. All right. I know everybody is, especially if you're in Gainesville, you're dealing with some crazy weather right now. If things lag out for you, don't stress too much. I'm recording locally on my machine, not on the cloud. So the quality of the recording will be good, and I'll get it up as soon as I can after class. But try to bear with me. If you have trouble hearing anything, again, just ask me to repeat. I'll be happy to repeat. The big thing that we're going to learn here in section 3.4 is called the rational roots theorem. And this is a tool that allows you to come up with a list of guesses. All right, so remember, we're trying to factor polynomials. We're trying to factor polynomials to find roots. That's sort of our deep goal through these last few sections. Sometimes that's really fucking hard. No nice way to say it. Sometimes you look at those factoring tricks I showed you in the last class, none of them work or none of them apply. The polynomial in question isn't one that you've seen before. You don't know how to factor it using some other outside trick. But you know that you can check to see if something is a root using synthetic division. So we talked about this last time, right? You synthetic divide by that X minus C factor. And if that remainder comes out to be 0, then boom, you found a root, and you also get the coefficients of the quotient polynomial for free. It's a great process. The question is, how do you know what to check, right? You know how to test one number at a time, and you don't have to plug in, you just use synthetic division, but how do you know what to check? And the answer is this theorem called the rational roots theorem. Your book calls it the rational zeros theorem, but everybody else calls it the rational roots. All right, parentheses, zeros. Yeah. This says if the polynomial, I'm going to write it out in general here, P of X equals an x to the n plus n minus 1, x to the n minus 1 goes all the way down like this, a1x plus a0. So if you have a polynomial has any rational roots, then those roots, those rational roots must be of the form plus or minus p over q, little p over little q, different than the p for the polynomial, where p is a divisor of the constant term A naught, and Q is a divisor of the lead coefficient. So what this theorem does is it supplies you with a list of possible rational roots. You look at your constant term and you look at your lead coefficient, you find all of their divisors, all of the numbers that evenly divide those, and then you form all the possible ratios where the top is a divisor of the constant and the bottom is a divisor of the lead coefficient. So let me just give you an idea here. I can say list all possible rational roots for, how about p of x equals x cubed minus 3x plus 2. Okay? So here's what you do. You take your constant term, which here is 2, and your lead coefficient, which here is 1, and you list all of your p's and q's. So your p's are divisors of 2. And 2 is prime, so that's just plus minus 1 plus minus 2. Your q's are divisors of the lead coefficient here, which is 1. And that's just plus minus 1. The only integers that divide 1 are 1. So the list of all possible rational roots you take every possible p over every possible q. So here that's just plus minus 2 and plus minus 1. All right, so you divide by 1, nothing happens. You don't have to list the plus and minuses here if you don't want to. You can just think of positive divisors, and as long as you do them here, you're fine. So there's 4 possible rational roots according to this theorem for this polynomial. That's the problem done. Now, if I want to, as a separate example, I could check each possible rational root from the previous example. And try to factor the polynomial p of x. And this is something that you're going to be doing a lot of in your homework. So if I want to check rational roots or check any roots in here, the best way to do that is with synthetic division. So I can check, for example, 1. If I want to know if 1 is a root, then I'm going to synthetic divide this polynomial by the polynomial x minus 1. Remember how the synthetic division works. You write the coefficients of p down. So that's 1x cubed plus 0x squared minus 3x plus 2. And I like to put this little bar here to remind myself what it is I'm doing. I'm doing division. You bring this guy down, and then you multiply these two. 1 times 1 is 1. And then you add these. 0 plus 1 is 1. 1 times 1 is still 1. Here, and then you add. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. And when you add 2 and negative 2, you get 0. So my remainder is 0. Therefore, x equals 1 is a root. Therefore, x minus 1 is a factor. And that's all coming from our TF8, right? Remainder is 0 means that's a root, means that's a factor. And what's more, the quotient polynomial, these are the coefficients of the quotient. So I learned that x cubed minus 3x plus 2 can be written as x minus 1 times, right, that's the x minus 1 factor, times the quadratic with these coefficients. So that's 1x squared plus 1x minus 2. X squared plus x minus 2. And this is the polynomial p of x. So we've succeeded in beginning to factor, and then once you extract a factor, you start back over with the quotient and ask, okay, well, what can I do to factor this? If this was still like a big polynomial, degree 3, 4, whatever, I would probably come back through my rational roots theorem. But since it's a quadratic, I've got lots of other tricks. I can factor this nicely. This is x plus 2 times x minus 1. This is x minus 1 times x plus 2 times x minus 1. And then if I want to write this neatly, I would write it as x minus 1 quantity squared times x plus 2. Like that. So you see what we just did? We just factored the polynomial x cubed minus 3x plus 2, which is a pretty tricky guy to work with, by using the rational roots theorem to come up with a list of possible rational roots. You check the elements of that list using synthetic division one at a time until you find something that works. Here, the first thing we checked worked. And then that gives you a factor and the quotient. And then you just start back over on that quotient polynomial, which here we were able to factor further by hand. I could now use this to draw the graph. All right, a combination of end behavior roots and their multiplicities is all you need for a graph. We saw that last week. There's lots and lots of other things we could do. But the purpose of this lecture is to just get you through the factoring. So questions on, whether it's not, questions on what we've done in these two examples. Please speak loudly. Oh, no. Sorry, we're looking for the cat. She might be outside. Any questions on where I got this list? The four numbers here. 2, 1, -2, and -1. Any questions on what I'm doing here? The synthetic division?
Why did you use synthetic division?
Because it's faster than long division. So if I want to check if a certain number is a root of my polynomial, the fastest way to do that is to synthetic divide my polynomial, here's the coefficients of my original polynomial, by the polynomial x minus that number. So what I'm doing here, let me annotate. Here I'm dividing p of x equals x cubed minus 3x plus 2 by, I'll call it d of x, because that's what we were using for notation before, equals x minus 1. So this is the x minus 1 guy. This is how he's represented in the synthetic division. Remember, you just put the number here that would be the root. And this is p of x. These are the coefficients of p. So 1x cubed, 0x squareds, minus 3x plus 2. But the synthetic division is here to check and see if x minus 1 is a factor, to check and see if 1 is a root. I
So
thought,
it was -1?
so the number that goes here is the number that you're checking to see if it's a root. And 1 is a root means x minus 1 is a factor. All right, c is a root if and only if x minus c is a factor. That's kind of,
I got it. I got it.
all right, cool. If one didn't work, if this remainder came out to something other than 0, I would throw him out and try something else from this list, either 2 or -1 or -2. And I would keep going like that, synthetic dividing, until I got something that gave me a remainder of 0. Once I get that, then I know how to start factoring, because that gives me this.
Can you explain again how you got 2 and 1, like for the first example?
So I'm following my rational roots theorem. It says, if a polynomial has any rational roots, those are roots that can be written nicely as fractions, whole numbers or fractions with whole numbers, then those roots have to be of the form a divisor of the constant term over a divisor of the lead coefficient. So when I look at this polynomial, I ask, what are all the divisors of the constant term? Well, the constant term is 2, so its divisors are just 1 and 2.
Okay.
And then I ask, what are all the divisors of the lead coefficient? Well, the lead coefficient is 1, and the only divisor of 1 is 1.
All right, I got it.
Yep, and we take those with plus and minus. So if your problems in your homework say just list all the possible rational roots, we can do one more like that. Yeah. I won't go on to then factor this, but I will just list all the possible rational roots as an exercise. So here my polynomial p will be 2x cubed plus x squared minus 13x plus 6. I'll switch to a PP&D. I'll switch to purple here for the solution. Sorry. So my possible rational roots, I know I have to find my p's and my q's. P's are going to be divisors of 6. Q's are going to be divisors of 2. Luis, you okay? We've either got a cat walking on Luis's keyboard or he's passed out face down on the keyboard. One of those would worry me. Sorry, it's getting funny things in chat. All right, for now I'm going to continue. Divisors of 6. So what numbers, what integers divide 6? Well, 6 itself, 3, 2, and 1 all divide 6. Divisors of 2, just 2 and 1. So if I form all the possible ratios, taking anything from this list and dividing it by anything from this list, here's how I do it. I take every guy here and divide by 2. Then I take every guy here and divide by 1. So our possible rational roots these are plus and minus 6 over 2, plus and minus 3 over 2, plus and minus 2 over 2, and plus and minus 1 over 2. That's all the ratios over 2. And then you go plus minus 6 over 1, plus minus 3 over 1, plus minus 2 over 1, and plus minus 1 over 1. So you've got 1, 2, 3, 4, 5, 6, 7, 8 things here, but they're not all distinct. Some of these are overlapped, right? So let me relist these. That's plus minus 3, plus minus 3 halves, plus minus 1, plus minus 1 half, plus minus 6. See, now I've got 3 over 1, that's 3 again, so I'm not going to relist that. 2 over 1, that's the first time that's shown up here. So plus minus 2 and plus minus 1. So this is my possible list of rational roots. I've got 1, 2, 3, 4, 5, 6, 7 times 2, plus and minus each, 14. 14 possible rational roots. And if I wanted to factor this polynomial, I would start checking those one at a time. And it's going to take a while because you got to do, in theory, you know, maybe only one of the roots is rational and the other two are irrational. So you could check 13 different things with synthetic division before you find the one that works. It's even possible that none of the roots are rational, right? And there has to be a real root here because it's a degree 3 polynomial and those always cross the x-axis at least once. So there's got to be at least one real root, but maybe they're all irrational. Now, I wouldn't do that to you on a homework set or on a test. I just want to point out that it's a possibility. But if we wanted to factor this polynomial, the next step would be to start checking things from this list. And you check them one at a time using synthetic division until you find one that works. And then that will give you the quotient polynomial, and you start over with that quotient polynomial.
So you divided the p's by the q's. Is that what you just did?
Exactly. We take every one of these, or every combination of something from this list divided by something from this list. And that's what our theorem tells us to do. Take all possible divisors of the constant over all possible divisors of the lead coefficient. That will give you your list of possible rational roots. Bit of a pain in the ass. No lie, bit of a pain in the ass, but it works really well. So because this is a bit of a pain in the ass, we would like tools to help us save time. Wouldn't it be nice if I could just throw out half of these? Say none of the negative guys could be roots. This is a theorem called Descartes' rule of signs. And I guarantee you've heard of this guy, Descartes. Although maybe nobody told you he was a mathematician. Everybody has heard the phrase, I think, therefore I am, right? Cognito ergo sum in Latin. That's this guy, the philosopher René Descartes. In addition to having some pretty clever ideas like thinking implies existence, I think, therefore I am, he's the reason we call the XY plane the Cartesian plane. That comes from his name, Descartes, Cartesian. In addition to all that stuff, he came up with this pretty cool theorem called Descartes' rule of signs, which tells you how many positive roots a polynomial could possibly have based on the number of sign changes in the polynomial. So I'll be real clear about this in just a second. Let me first tell you the theorem. So if p of x is a polynomial with real coefficients, then you've got two possible cases, or two kind of useful facts. The number of positive real roots is either equal to the number of sign changes or less than that by an even whole number. And this is written in standard form. Right, written as in the definition of a polynomial. A sign change is like this, right? From 2x cubed to x squared, as I come down one term, this is positive and this is positive, so there's no sign change. From x squared to minus 13x, coming down one term, this is positive, this is negative. That's one sign change. And then coming from minus 13x down to plus 6, that goes from negative to positive. That's two sign changes altogether. So does everybody understand what I mean by a sign change? This polynomial has two sign changes. Plus to plus, no sign change. Plus to minus, there's a sign change. Minus back to plus, there's the other sign change. So Descartes' rule of signs says that a polynomial with real coefficients either has the number of positive real roots is either equal to the number of sign changes or less than that by an even integer. And there's another way of thinking about this that has to do with transformations of graphs that I'll share with you, but really this is the deal. I'll go ahead and share with you the other one. The number of negative real roots of p of x is either equal to the number of sign changes in p of negative x or less than that by an even number. And the second thing is really a consequence of the first. P of negative x is what you get if you flip p of x over the y-axis. So if something was a positive root before, when you flip it, it'll be a negative root. If something was a negative root before, when you flip it, it'll be a positive root. So here, this is just the horizontal reflection, the reflection over the y-axis of the original. So you're applying the same rule, rule 1, but to the reflected polynomial to get rule 2. I want to show you this in action. And then we'll combine it with the rational roots theorem to see how much more quickly we can do this shit. So let's do it. I'll hold here for a minute. I know there's a lot to write. While we're waiting, is Luis back? Luis, you doing okay, bud? Mr. Pardo?
I have a question.
Yes.
Is our exam on this info on Monday?
I haven't set the date for this test. We are a little bit behind, right? So I wanted to cover these sections last week. We're covering them today. So it'll be, I'll set the exam date when it's clear when we'll finish 3.7. I think probably we'll finish 3.7 Wednesday. I think 3.6 is going to take a good chunk of tomorrow. And so 3.7 probably will finish Wednesday. Which means the next exam will probably be next Monday is a reasonable guess, I think. I wouldn't want to do it any sooner than that because I'm not sure you guys will be ready for it in time. But maybe later this week, Wednesday and then exam Thursday because we don't have Friday. Yeah, next Monday. Safe to say exam 2 will be next Monday. Okay. So let's use Descartes' rule of signs. Find the number of possible positive and negative real roots p of x equals about 3x to the 6 plus 4x to the 5 plus 3x cubed minus x minus 3. So how many sign changes do we have here? This term is positive, and so is the one beneath it, so no sign change there. This term is positive, and so is the one beneath it, so no sign change there. This term is positive, the one beneath it is negative, that's one sign change. This term is negative, and so is the one beneath it. So there's only one sign change. Therefore, by Descartes' rule of signs, DRS, P of x has either one positive root or less than that by an even number. Well, if you, the smallest even number is 2. If you subtract 2 from 1, you get -1. It's not possible to have -1 real roots, positive real roots. Hence, P of x has one positive real root. Okay, what about negative real roots? To do that, we need to look at P of negative x, which is 3 times negative x to the 6, plus 4 times negative x to the 5, plus 3 times negative x cubed, minus negative x minus 3. And if you simplify this, negative x to the 6, because 6 is an even power, that's the same as x to the 6. This is 3x to the 6. Negative x to the 5, the negative pops out because that's an odd power. So it's going to be minus 4x to the 5. Again, this is an odd power, so this negative will pop out. We'll have minus 3x cubed. And then minus minus here makes plus, god damn these purple pens, plus x minus 3. So this is P of negative x written in standard polynomial form. How many sign changes here? Well, from this term down to this term, there's one sign change. No sign change here, negative to negative, negative to positive again, one sign change. And then positive to negative again, there's one more sign change. So there's 1, 2, 3 sign changes. So by Descartes' rule of signs, P of x has either 3 or less than that by an even number. The only even number you could subtract from 3 and still have a non-negative number is 2. So, or 1 negative real roots. All right, and the idea is you can use this to narrow down your list of possible rational roots. If we cooked up the list of possible rational roots for this guy, divisors of 3 over divisors of 3, that's 3 and 1 over 3 and 1, all those permutations, it's 4 of those with signs. But we know that, of those 4, 2 would be positive, but we can only have one positive root. If you had a big long list, but Descartes' rule of signs tells you can only have negative real roots, you can't have any positive real roots, then you just ignore all the positive ones, or vice versa. If Descartes' rule of signs tells you can't have any negative real roots, only positive real roots, you ignore all the negative ones. So that's a useful tool, Descartes' rule of signs, surprisingly useful. But that's really it, guys. That's really all we have in section 3.4. We're just trying to hook up all of these possible roots, all of these, we're trying to figure out how to factor polynomials. And the rational roots theorem, together with synthetic division and Descartes' rule of signs, is the main tool. In practice, Descartes' rule of signs sometimes saves time, sometimes it doesn't. If you don't have a lot of sign changes and you do have a big list of possible rational roots, then I recommend using Descartes' rule of signs. Otherwise, just use the rational roots theorem. So let's see. Let's find all the real zeros for some polynomial. We did one like this. Let me take some guy that's not super easy, but not super hard. Something right around. How about x to the 4 minus 6x cubed plus 4x squared plus 15x plus 4. So I want to find all the real roots. I want to factor. In other words, give the factored form and state all the real roots. I can look at my Descartes rule of signs. I've got one sign change, two sign changes, two sign changes. So I've either got 2 positive real roots or 0 positive real roots by Descartes rule of signs. But let's use my rational roots theorem. I'm going to stick to the black pen here because my purple pens are being shitty today. I got to find all the p's and the q's. P's are divisors of 4, so that's 4, 2, and 1. Q's are divisors of 1, that's just 1. So my possible rational roots, those are plus minus p over q, where p comes from that list, q comes from that list. That's plus minus 4, plus minus 2, plus minus 1. And again, I want to say p of x has either 2 positive real roots or 0 positive real roots. So if I start checking these off, and I somehow come down to the fact that the remaining ones have to be positive real roots, and there's more than 2 of them, I know that I've made a mistake. 1 is usually pretty easy to check. I recommend checking 1 by plugging in rather than by synthetic division. So we can start checking. P of 1 is easy to evaluate. It's 1 minus 6 plus 4 plus 15 plus 4. So what is that? 15 and 4, that's 19, plus 4 is 23. 23 minus 6 is 17. 17 plus 1 is 18, which is not 0. So x equals 1, not a root. From here, synthetic divide. So next I'll check x equals -1, which means I'll use my synthetic division. I'll put the possible root over here and then list the coefficients here. Those are 1, -6, 4, 15, and 4 again. I bring the 1 down. -1 times +1 is -1. I add those, I get -7. -1 times -7 is +7. I add those, I get 11. -1 times +11 is -11. I add those, I get +4. -1 times +4 is -4. I add those, I get 0. Hey, we win. So -1 is a root. Right, here I'm checking x equals +1. And I did that by plugging in rather than by synthetic division because it's quick to just plug in 1.
I have a question.
Yeah.
For the 7, wouldn't that be -7? So would that be -3, not 11?
Oh, shit. No. Nope. So -6 plus -1 is -7. -7 times -1 is +7.
Okay, so you times it by the -1, not the regular one up there.
Yeah, each cycle we multiply by this. So I bring the
Okay.
1 down, multiply by -1, that's this. Add those, get -7, multiply by -1, that's this. At each cycle, we're multiplying by this guy. Had me nervous though, I do make mistakes, it happens. So what this tells me is that P of X has -1 as a root, which means X plus 1 is a factor. And then the coefficients of the quotient are given by these numbers down here. So that's, I'm taking a degree 4 and dividing by degree 1, that'll be a degree 3. So that's x cubed minus 7x squared plus 11x plus 4. And what we would do with this guy is repeat the same procedure. So I want to continue factoring my polynomial p. I've managed to extract one factor corresponding to that root -1. And then I need to check this guy. I kind of start over with this guy as my base polynomial. He has the same constant term and the same lead coefficient, so he has the same p's and q's, same list of possible rational roots. Should I check -1 again? Is it possible that -1 is also a root of this?
It's possible.
Yeah, it certainly is, right? If -1 was a multiplicity 2 root of the original, then it could be that it's a root of this guy as well. Should I check +1 again? Is it possible that +1 is a root of this?
No?
Good, why?
Because it's a factor.
Well, imagine +1 was a root of this. Then it would have given us 0 here, right?
Yeah.
Yeah, that's the idea. So we already know that this guy doesn't have a factor of x minus 1. And if this guy had a factor of x minus 1, so would this guy. But since we know this does not have a factor of x minus 1, we know that this doesn't have a factor of x minus 1 either. So I don't need to check 1 again, but I do need to check -1 again. So we'll just keep going. So now we start over with x cubed minus 7x squared plus 11x plus 4. And if you see a faster way to factor this, by all means use that. But right now it's still a cubic. So we're going to check -1, and this is 1, -7, 11, 4. -7, 4. Bring this down. 1 times -1 is -1. Add those, that's -8. -1 times -8 is +8. Add those, that's 19. 19 times -1 is -19. This definitely ain't 0, right? No, that's -15. So this is no good. So we checked x equals -1 and no dice. So we move on to the next thing on our list. We've ruled out both plus and minus 1. Now we should look for our 2's. So let's check x equals +2. So 2, 1, -7, 11, 4. Bring down the 1. 2 times 1 is 2. It's -7, it's -5. 2 times -5 is -10. Sum those and you get +1. 2 times 1 is 2. Sum those, you get 6. No luck. So this is also not a root. We can check x equals -2. -2, 1, -7, 4. Bring down the 1. 2 times -2 times +1 is -2. those, that's -9. -2 times -9 is +18. Add those, that's 29. Times -2 is 58. -58. +4 is -54. So again, no luck. So we've checked +1, -1, 2, and -2. We're on to the 4s now. 4, 1, -7, 11. 4. Bring this guy down. 4 times 1 is 4. -7 and 4 is -3. 4 times -3 is -12. -12 and +11 is -1. Hey, I think we're in luck. 4 times -1 is -4. Sum those, you get 0. Yay! Okay, so what that tells me is this polynomial can be rewritten as x cubed minus 7x squared plus 11x plus 4 is equal to x minus 4, because 4 is a root, times the guy whose coefficients are given here. That's x squared minus 3x minus 1. And putting this together with what we already knew, we now know that p of x, which we saw was x plus 1 times x cubed minus 7x squared plus 11x plus 4, must be x plus 1 times x minus 4 times x squared minus 3x minus 1. And now we've got this down to some linear factors that we know and a quadratic guy. So if I can factor this guy, I factor him. If I can't, then I call it a day and say he's irreducible. Two numbers whose product is -1 and whose sum is -3. Certainly no integers are going to do that. We can check to see if this will factor using the quadratic formula. So I want to know, is this irreducible over the reals? Does this have any real roots? The roots would come from the quadratic formula. Which here would be 3 plus and minus the square root of b squared, which is 9 minus 4 copies of 1 times -1, all over 2 times 1. So that's 3 plus and minus the square root of 9 plus 4, which is 13. So there are real roots there, they're just not nice. So that's not irreducible. Irreducible here would mean complex numbers out. The roots are 3/2, I forgot my purple die, plus the square root of 13 over 2, and 3/2 minus the square root of 13 over 2. So if I want to fully factor this polynomial, which again is my goal, then I would say p of x is equal to x plus 1 times x minus 4 times the factors from this quadratic, which come from these roots. That's x minus 3/2 plus root 13 over 2, and x minus 3/2 minus root 13 over 2. Again, just coming from that TFAE. If you find a root, there's a factor. If you find a factor, there's a root. We found these roots. So each one gives a factor. It's always x minus that thing, x minus that thing. So here is your fully factored form. It's not pretty, but that's it. Questions on this?
What does it say in purple under x squared minus 3x minus 1?
Irreducible over reals? Can this be factored using real numbers? That's what we're asking there. So is this irreducible over the real numbers? Irreducible means can't be factored. So if it's the case that this can't be factored, then I would stop here because I just want to find the real roots. But if it's the case that this can be factored, then I do want to factor it, and that's what we've done here. So believe it or not, if you multiply this out, you will get x squared minus 3x minus 1. Take a little bit of work, but you'll get there because those are the roots.
So that's how we check it if we want to find out that's a fact, if it have any real roots.
Yeah, yep. So looking at this form right here, I can tell you I've got at least 2 real roots, the roots associated with these factors, -1 and +4. But looking at this, I can't tell you right away, does this have any real roots? Kind of think about this quadratic as its own function. It's a parabola. Does that parabola cross the x-axis or does it sit entirely above it? It's not immediately clear until you plug into your quadratic formula. Does that make sense?
Yes.
Okay. There's really not too much else for me to tell you guys about factoring polynomials besides when you get to this step, even if this thing doesn't have real roots, you can still keep going. You just use the complex roots instead. So I'll show you the theorems and give an example of this next section. But then I think we'll probably be done. Yeah, done with these bits. So we want to talk about complex conjugates, but that's all.
I have a question.
Yeah, sure.
So the answer for the question, it would be the equation underneath the P of X, right?
So the complete factored form is this thing right here. This would be your answer for the complete factored form. And the roots
Okay.
would be x equals -1, 4, and these 2 weird numbers, 3/2 minus the square root of 13 over 2, and 3/2 plus the square root of 13 over 2.
Got it.
All right. So here's section 3.5. And this is on fundamental theorem of algebra. And complex roots of polynomials. All right. Here's the gist. The fundamental theorem says I think I've been talking about the same sort of thing in my differential equations class. So I don't remember if I shared this with you. I don't think I have. It says a polynomial of degree n always has n roots when counted with multiplicity. That's it. So a polynomial of degree 3 always has 3 roots when counted with multiplicity. Polynomial of degree 2 always has 2 roots when counted with multiplicity. And these may be, these roots, may be real or non-real complex numbers. And the rules before about factors and theorems still hold, or sorry, factors and roots still hold. So whether the roots are complex or real numbers, you still having this rule that says if you have a root, you have a factor. If you have a factor, you have a root. Let me show you an example. Factor p of x equals x cubed minus 2x plus 4 completely. All right, we're going to do the same thing we did before, where I use my rational roots theorem to try and extract a real factor. It's a cubic polynomial. Cubic polynomials, because of their end behavior, one side goes up, one side goes down, have to cross the x-axis somewhere. So there's always at least one real root. We hope that it's rational. So we apply our rational roots theorem, the p's and q's. P's are divisors of 4, that's 4, 2, and 1. Q's are divisors of 1, that's just 1. So our possible p over q stuff is plus minus 4, plus minus 2, and plus minus 1, right? When you divide by 1, it doesn't change anything. I can check using synthetic division. If you plug in positive 1, you see right away it doesn't work. 1 minus 2 plus 4, that's not 0. So p of 1 is 1 minus 2 plus 4, which is 2 plus 1 is 3. It's not 0. So then I'll check negative 1. Again, I need to be careful with my synthetic division. So negative 1, the thing I'm checking. And then the coefficients of p, which are 1, 0, negative 2, 4, right? There's no x squared. So 1, 0, negative 2, 4. Bring him down. 1 times negative 1 is negative 1, plus 0 is negative 1. Negative 1 times negative 1 is positive 1, plus negative 2 is negative 1 times negative 1 is positive 1, plus 4 is 5, which is not 0. So nope. I checked positive 1 and negative 1. I'll check negative 2 next. So same thing, negative 2, the thing I'm checking, and then the coefficients of p, which are 1, 0, negative 2, 4. Bring down the 1, multiply by negative 2, add, multiply by negative 2, add, multiply by negative 2. Hey, we win. So negative 2 is a root. Therefore, p of x is equal to x plus 2, because negative 2 is a root, times, this is 1x squared minus 2x plus 2. So x squared minus 2x plus 2. And again, this isn't going to factor nicely, right? There are no two numbers that multiply to 2 and sum to negative 2. So I know this won't factor over the whole numbers. I can use my quadratic formula. Here, the roots will be x equals 2 plus and minus the square root of 4 b squared minus 4 times 2 times 1 all over 2a, which is just 2. So that's 2 plus and minus the square root of 4 minus 8. Okay, well, so 4 minus 8, that's negative 4 over 2. What's the square root of negative 4? Remember, we're allowed to play around with complex numbers now. Does anybody remember how you take the square root of a negative number?
2i.
Yeah, it's the square root of -1 is I. So the square root of -4 is I times 2. So there's a bunch of ways you could get there. This is 1 plus or minus I. All right, you can factor a 2 from the top and cancel at the bottom. Or you could write it as 2 over 2 plus or minus 2i over 2. But these are our two roots. So we get 1 plus I and 1 minus I. And that tells me how to factor this guy. So P of x, I'll say x squared minus 2x plus 2 on its own is equal to x minus 1 plus I times x minus 1 minus I. And pay attention to how I'm doing this, right? It's not x minus 1 plus I, x plus 1 plus I. It's x minus the thing, always x minus the thing. And then the things are 1 plus I and 1 minus I. Hence, P of x, my polynomial, is x plus 2 times x minus 1 plus I, x minus 1 minus I. That is this polynomial factored completely. Okay. Questions on what we did here?
I have a question on the very beginning step, the P's and Q's. So the P is the factors of 4, right, from the final term. And then is Q's always the divisors of 1? Or is it?
Always the divisors of the lead coefficient.
Oh, okay.
So here this is 1x cubed. The lead coefficient is 1. So always divisors of whatever the lead coefficient is. All right. So I have one neat fact for you, and then I want to practice one other problem type, and then I'll let you go. You notice 1 plus I and 1 minus I, those are what are called complex conjugates. So the complex conjugate of A plus IB is A minus IB. Definition, right? So e.g. 1 plus I has complex conjugate 1 minus I, or 2 minus the square root of 3 times I has complex conjugate. I just changed the I to negative I. I swapped the imaginary part for its negative. So this would be 2 plus the square root of 3 times I. The fact or theorem is that non-real complex roots of polynomials with real coefficients always come in conjugate pairs. So for example, if you know that 3 minus I is a root of P of x, then 3 plus I must also be a root. This makes for fun exam problems where I say, you know, find me a polynomial with real coefficients having roots -7, 3, and 2 plus I. Then you would need to remember that complex roots always come in conjugate pairs. So if 2 plus I is a root, 2 minus I has to also be a root. And then you can write down your polynomial. Let's try an example of that. Okay. So let's find a polynomial of degree 4 with real coefficients having roots I, 2, and -2 with lead coefficient 4. Okay. Who can tell me some factors of the polynomial I'm requesting?
Plus or minus I.
Also, so there's a root missing from the list. That's good. So since I is a root, so must be -I. That's good. That's the kind of sneaky thing here. And then remember, every root tells you a factor. So who can tell me the factor associated with the root 2?
X minus 2.
Yeah, exactly. X minus 2's got to be a factor because 2's a root. What else?
X plus 2.
X plus 2's got to be a factor because -2's a root. What else?
X minus I.
Very good. X minus I has to be a factor because I is a root. What else?
X plus I.
Very good, because we know -I also has to be a root. This is the one people miss. All right, so this could be P of X. But remember, you got to have this lead coefficient, right? This lead coefficient could be anything. So A times X minus 2, X plus 2, X minus I, X plus I. And then they told us, you know, this would work. And since the lead coefficient must be 4, we just say, okay, 4 times X minus 2, X plus 2, X minus I, X plus I. And we could multiply all this out. That's an option. I won't require you to do that on tests, but if instead of saying the lead coefficient has to be 4, I said, you know, P of 0 has to be 7 or something like that, then you would actually have to multiply this stuff out in some fashion. Or if I told you the coefficient of x cubed needs to be 5, then you would have to multiply this out in order to figure out what A needs to be to satisfy that criterion, like we saw last time. Same stuff, just now we're dealing with complex numbers. So just this one time, because in your homework, you will have to multiply some stuff out like this. I'm going to show you how to do it. The nice move, the two factors that come from conjugate pairs of roots, multiply those out first, right? You could, if you wanted to, FOIL these, then distribute this, then distribute this. Don't fucking do that. It's going to be a nightmare. If you multiply out the factors associated with the complex conjugate pairs, those will always get rid of the i's. The i's will go away. And then you don't have to deal with complex numbers anymore. Now, mathematicians, we love complex numbers. So I don't want to give you the impression that they're an unpleasant thing. But in order to make your life nicer, easier, I would recommend handling that stuff first. So x times x, you FOIL it just like normal. That's x squared. Your outers are plus ix. Your inners are minus ix. And your lasts are minus I times I, or minus I squared. So that's 4 times x minus 2 times x plus 2 times x squared. These guys in the middle add up to 0. What's I squared?
It's the square root of -1 squared.
Right. So if I is the square root of -1, then I squared is the square root of -1 squared, which is,
-1.
yeah, -1. I squared is -1. So that's minus -1, which is plus 1. So the factor, the roots of x squared plus 1, they're not real numbers. They're plus and minus I. They do exist. They're just complex numbers. Now you can FOIL these and then distribute everything. So this would be 4 times, this is x squared minus 4 when you FOIL it. This is x squared plus 1. So then if you distribute those out, you'll get x to the 4 minus 4x squared plus 1x squared, which is minus 3x squared. And then your last, which is minus 4. So if you wanted this polynomial written out, it would be 4x to the 4 minus 12x squared minus 16. But again, if I ask you this sort of a question on the test, just give me this. You don't need to do all of this. Unless for some reason, the extra condition here that you need to solve for A requires looking at one of the other coefficients, don't multiply it out. Okay. I could prove to you that complex roots always come in conjugate pairs. The proof isn't that hard, but I don't think it's very insightful either, not at this level, which means that's it. That's it. We're done. We're done with polynomials. And the homework that I have for you guys is going to be going up in just a few seconds. I wanted to try and trim a few problems out of it because it's going to be due on Wednesday. We're going to be moving kind of quickly this week because we are a little bit behind. Now that we have finished complex roots, we're going to talk about rational functions and nonlinear inequalities in some detail. And then we'll be ready for exam 2. So I think probably we'll get through 3.6 and tomorrow, 3.7 we'll definitely get through the day after. And then I'll set the date for exam 2, but I think probably exam 2 will be next Monday. That's probably how we're going to do this. We're going to have to move a little bit quickly through these. That'll be okay. Thursday, I'll probably cover at least one of these sections. And then the following week after the test, we're going to talk intensely about logs and exponentials.
I have a question.
Yeah.
So since we were behind because of the whole like day off of school because of the hurricane and everything, are we gonna like still have a final, or like what's that gonna be like since we're gonna be missing almost a whole week of like the sections because we're already on week 4?
Yeah, it sucks that we missed so much time that week between the holiday and the hurricane. The way this works, when I do 1140 and we lose a lot of time like that, there's a few sections where I can trim things, namely this stuff down here. So these are cool. They're fun. They're great, but they're not at all necessary for calculus. These sections in chapter 11 look at conics, but look at them from the perspective of like ancient geometry. So rather than thinking of a parabola as the graph of a quadratic here, we think of a parabola as like the locus of all points that are equidistant from a directrix and a focus. Fun, not at all necessary for calculus. So if we have to trim, we're going to trim this shit. I'll be doing my best to pace it so we don't have to trim too much down there. I do like to cover the binomial theorem a little bit. It's important we talk about matrices and sequences. So yeah, if we got to, I'm gonna trim the chapter 11 stuff at the end. It's a fair question. It's unfortunate. This, I think 2 or 3 years ago, we lost like a whole week to a hurricane in the fall. Had to do the same thing then. Sometimes it happens, and I promise I won't pull anything from the course that you guys need, and I won't shove stuff in faster than you can handle it. So if we have to, we'll just pull out material you don't need.
Awesome. Thank you.
All right, any other questions before I let you guys go?
Are you having office hours today?
I
Is
am.
it for the test? The makeup test?
Well, both. So I'll be doing my office hour, and the people who are taking the makeup test, I'll be shoving them into breakout rooms where they can work. But I'll be in the main room doing office hours.
Thank you.
All right. Anything else before I let you guys go? Alrighty then, that's it from me. I hope you guys have a lovely rest of your day. If you need to talk, come by office hours. Otherwise, I'll see you tomorrow.